Yeah.
Well, oh, okay, wait there, hang on.
Yeah, I am.
Okay, so a long time ago, we zoom in, Chelsea. We were trying to work out the area underneath a curve. Let's say x squared. Okay.
Okay.
So let's say we're going to cut up into 4 strips. So we would jump to here, work out the height, and then times it by the width. Remember this? We did it last time.
I mean, I remember, but I don't know how to do it.
Okay. So let's say we're trying to work out the area from 2 to 10 underneath a curve. Okay.
Okay.
And then we're going to use 4 strips for the time being. N equals 4. Later on, we can make this to 1 million strips. Okay. But for the time being, let's just say 4 for simplicity. So what's this delta x here? What's this width here? Delta x. Do you know what? Remember, we're trying to work out the area from 2 to 10, and we're going to cut it into 4 strips. So what must be the width of this strip?
8.
No, 8 is from 2 to 10. That's 8.
Yeah.
I want to know the width of one strip.
Oh. 2.
Yeah, because you would get this length and then cut it into 4 strips, right? So 8 divided by 4. So delta x is actually 2. Okay, Chelsea.
Okay.
All right. So we know that width. So we know the width is 2. What is this x location right here? Because I want to know this green length now. What's this green height? What's that? You got to somehow work out that green height. What's that green height? What's that green height?
The length is, or the width is 2.
Yeah, okay.
The height is, let me think. It's 4.
Not the scale. Yeah, what? The height is 4. Is it? No. You see, this here, well, this purple height here is 4 because when you put 2 into the function, when you square it, it will then jump to
it's 16.
Yeah, it's 16. Okay, that green length is 16. So we would get 16. So what's the width? What's the area? What's this green area? So this looks 4. When you square it, it will give you 16.
16.
But what's the area of that green rectangle?
4.
What do you do to work it?
Let me think.
Sorry?
I'm thinking. Hold on. Would you do 16 times 2?
Yeah, because you would get 16 times delta x, which is this width here.
Yes.
Right? So that would then give you, what is it? 32. That's the area for this green strip. And then we would start from here and then jump twice. What's this location here?
Where?
What's the x location? What's the x location? What's this
6?
blue location here? Sorry? 6, yeah.
On a 0.
And then what's the blue height?
36.
Yeah. And then what's the area? So the
72.
height is sorry?
72.
No. 72, yeah. So this would be 72. And then you start from here, jump 3 times, and then work out the height. Eventually you can sum up this rectangle. Can you see that?
Yeah.
And then we can sum up this rectangle and then add up all the rectangles. That will give us a rough area of that area underneath that curve. But then that's only for 4 strips. So if we want to increase the accuracy, we would make n to be 1 million, so it gets more and more accurate. Okay, but the point is there is a way of finding out the area underneath a curve. Okay, Chelsea. But now I'm going to show you a much faster and better way of doing this. So let's say you're trying to work out the area underneath x squared from 2 to 10. Okay, Chelsea?
Okay.
Well, someone noticed that. Well, don't worry about the symbols for the time being. If you're trying to work out the area from 2 to 10, you of that graph x squared. Don't worry about this dx for the time being. Okay, Chelsea.
Okay.
Someone noticed that if you can find something that will differentiate to this, that will allow you to work out the area underneath the graph. So, for example, someone noticed that, well, if you can find something that differentiates to give you x squared, can you find something that would differentiate to give me x squared? Can you make a guess? There is something that when you differentiate it, gives you x squared. What is it?
Square root of x?
Square root of x. Hang on. So square root of x is really x power half. Okay, Chelsea. When I differentiate this, the half will come down, the x will stay the same, the power gets much.
Oh.
That's no good. That is nothing like x.
2x.
Wait, hang on.
Wait, no, not 2x, not 2x. Oh, 1 over negative x over, or 1 over negative, no, wait, hold on.
What?
1 over negative x over 2, or not over 2, but to the power of 2.
Well, is this what you're saying?
Yes.
Okay, so for me to differentiate this, I'm going to move the minus up. Okay, Chelsea.
Okay.
And then I'm going to try and differentiate this. That is the same as x to the power of minus 2. Do you agree?
Oh, okay.
Because if I were to give you x to the power of minus 2, you don't understand what it means to have a power of minus 2. So you
I don't know.
squared, right?
Okay.
Okay. So now when I try and differentiate this, Chelsea, look what happens when I try and differentiate this. Because currently, this is exactly the same as this. Do you agree? Do you agree?
Wait. Yeah.
Those two are actually the same as each other. Do you agree?
Okay.
Yes
Okay.
or no?
Yes.
Yeah. So now when I differentiate it, look what happens. Hang on. I'm going to try and differentiate this. So the minus 2 will come down. That will give me a positive 2. The x stays the same, right?
Yes. Okay.
But then the power gets minus by 1. So that you see this is nothing like x squared. There is something that when you differentiate it, it gives me x squared. And it's definitely not what you said. Here. Have another guess.
I don't know.
You don't know. Okay.
No,
Well,
I'm thinking.
there is something in such a way that when you differentiate it, it gives you x squared.
1 over 2x.
No. Well, wait
No.
there.
I changed my mind.
Try and differentiate x to the power of 5. What does that give you?
5x 4.
5x to the power of 4. Try and differentiate x to the power of, let's say, 9. What does
Oh,
that give?
Okay, I got it. Let me think. Hold on. Hold on. 1. Or hold on. Yeah, I don't know. I don't know.
Okay. Try and differentiate x.
9x 8.
Not, yeah. Can you see that every time you differentiate, the power decreases by 1 each time?
Yeah. Mm-hmm.
So it kind of makes sense. So you're looking for something that when you differentiate it, it gives you x squared, right?
Mm-hmm.
So maybe a good guess would be something of the line of x to the power of 3. Because when you differentiate it, the power gets minus by 1. Innit?
Yes.
All right, differentiate x to the power of 3 for me. What does that give you?
2x.
No, the power gets, you drag the power down.
3x2.
3x squared,
Yes.
right? Oh, look,
Yeah.
that's very close to x squared, but you don't want that
Yeah.
3. So you would go back to your initial guess and stick a third in here, Chelsea.
Oh.
So
Oh.
now, when you try and differentiate this, well, you leave the third alone, and then the 3 will, so that's one block. The 3 will come down, the x stays the same, the power gets minus by 1. And look, these two cancel each other out. Yay or nay?
Yay.
So that will then give you x squared. Do you agree?
Yes, I do. That's
Okay.
yeah.
So someone noticed that for you to work out the area, you would need to basically, what they would say, integrate x squared. Well, what integrate means is you've got to look for something in such a way that when you differentiate it, it gives you x squared. Basically, it's the opposite of differentiation. Are you okay with that?
Sure.
Okay. So wait there, Chelsea. So for you to work out that area, you would need to integrate it, whatever that means for the time being.
Mm-hmm.
Don't worry about all the symbols. I will explain it in the future. So it would be a third x squared from 2 to 10. Okay, Chelsea?
Mm-hmm.
And then here you've got a fraction, and then you're timesing a block, so it gets multiplied to the top. So I can write it as x squared over 3 from 2 to 10. Are you okay with that?
Yes.
Now, here's a weird thing, Chelsea. To work out the area, someone discovered that if you put a 10 into the x, that would be 10 squared over 3. And then you take away, and then you put the 2 into here. So that would be 2 squared
Wait.
over 3. That will then give you the
Wait,
area.
I'm trying to. I'm thinking. Hold on.
Sorry,
Okay,
what?
so hold on. Let me think real quick. Wait. So the 10 goes to the x squared.
Wait.
Where?
You put 10 into the x.
Yeah.
Yeah.
Oh,
So
so
that,
then it would be 100.
so yeah,
So
that
where do
would
you
be
put the 2?
wait.
The
That would be
subs.
100. And then you always take away, and then you put the 2 into the x.
Oh, so it would be 4 over 3.
Yeah, 4 over 3.
Oh, okay.
And then that will then give you the area. So the area is
Area of what?
96 over 3. The area underneath x squared between 2 and 10. If you go back to the
Oh,
diagram,
yeah. I see what
and
you mean.
someone discovered this, okay, we don't, in the future, we will try and understand why, but for the time being, we're just going to use it without understanding why it works. Someone noticed that if you integrate this thing, that would then allow you to work out the area underneath that graph.
Mm-hmm.
Yay or nay?
Yay.
Okay, let me give you another one. So let's say, can you remember what x to the power 3 looks like?
Yeah, I do.
What does it look like?
It's my favorite one.
Okay, what is it? It's your favorite one that you always get wrong. X to the power 3 looks like this. Silly Billy.
Oh, wrong way.
Okay, so now let's say you're trying to work out the area from 3 to 10, not to scale. So what's this area, Chelsea? So the area equals the integral of the function that we're talking about, which happens to be x to the power 3 dx. Okay, Chelsea, from 3 to 10. And you don't really understand this for the time being. I'm just asking you to accept it.
Yeah.
Okay, Chelsea.
Mm-hmm.
So for you, if you want to work out the area, you would have to integrate this thing. So what that means is you've got to look for something. You've got to look for something in such a way that when you differentiate it, it gives you x to the power 3. So can you hazard a guess?
Yeah. It's going to be 1/4 x4 to the power 4.
X to the power 4. I'm just going to multiply this x to the power 4 to the top. So give me x to the power 4 over 4 from where to where, Chelsea?
From 10 to 3.
Oh, from 3 to 10.
Yeah.
Okay, Chelsea?
Mm-hmm.
And then now you've got to do this, Chelsea. Put the 10 into the x. So that will give me 10 to the power 4 over 4. And then take away what, Chelsea?
Hold on, let me think. 3 to the power 4.
Yeah, and then you put a 3 into the x here. So that would be 3 to the power 4 over 4. And then do whatever you have to do. That would be your area. Right, Chelsea?
Okay.
It's kind of weird that for you to work out the area, who on earth would have thought that you need to find something that differentiates to the function in order to give you the area? But someone discovered it. We're just going to use it. Okay, Chelsea?
Mm-hmm.
Okay, what about this one? Square root of x. What does that look like as a graph? Oh, scroll up a bit, Chelsea.
I don't know what school. Actually, wait.
If you don't know, put it in your mind. What's 0 square? What's the square root of 0?
Pardon?
What's the square root of 0? What's the square root of
0?
Yeah. Yeah, so it's right there. What's the square root of 1?
1.
What's the square root of let's say 4?
2.
What's the square root of let's say 9?
3.
Yeah, so it looks like this. Oh, what's the square root of negative 4?
You can't do that?
Yeah. So basically nothing, we don't really care about what happens in the negative realm. Okay? So the square root graph looks like this.
Okay. Oh, yeah.
So hang on. So square root graph will look something like this. So y equals square root of x. So let's work out the area from 0 to, let's say, 100. What's this area here, Chelsea? What's that area, Chelsea? Oh, Chelsea, when we did this, Chelsea, we would split up with lots of strips. Remember this?
Yeah.
So it was something like area equals, we would sum up all the, we would jump to the function f of x, and then we would times it by the width, delta x, and then we would sum up all the rectangles. Remember that, roughly speaking? Can you remember that? Yeah,
Not really, no.
No? Okay, so, okay, so for time, let's leave this for the time being. Let's just try and work out the area underneath that square root graph. What's this area here? So area is the integral of what goes in here, dx, Chelsea. And you don't understand this dx thing. Don't worry about it for the time being. So what's
Square
the
root of
area?
x.
So square root of x goes in here.
And you have to like differentiate that or like
integration
it.
Integrate. From where to where, Chelsea?
From 0 to 100?
From 0 to 100. Yep. So now you've got to integrate it. So integrate it from 0 to 100. So now, Chelsea, you've got to look for something. So you are trying to integrate it now. What that means is you've got to look for something in such a way that when you differentiate it, it gives you x to the power of a half. Can you see that, Chelsea? Because the square root is to the power of a half. Okay. Did you know that?
No.
Did you know that?
Yeah, I did.
Okay, so what is it that will differentiate to give you x to the power of a half? Can you make a guess?
Wait, say that again? Wait, I thought it... What?
Square root is x to the power of a half.
Yeah.
Okay, you've got to look for something in such a way that when you square root it, when you differentiate it, it gives you the square root of x. What is it? There is something out there that when you differentiate it, it gives you x to the power of a half. What is it? Do you know, Chelsea?
No.
Okay, hang on. Let's say I'm asking you to integrate x to the power of 5. How would you do it? You've got to look for something in such a way that when you differentiate it, it gives you x to the power of 5. How would you go about doing that? So I'm asking you to integrate this for the time being. How do you integrate x to the power of 5?
5x to the power of 4.
5x to the power of 4. That's how you integrate it, right?
Yeah.
Okay, so you're saying 5x to the power of 4. When you differentiate that, does that give me x to the power of 5? Okay.
If I what?
Differentiate this. Does it give me x to the power of 5? Okay, differentiate
No.
this for me. That will then be 20x to the power of 3. I want you to find something in such a way that when you differentiate it, it gives me x to the power of 5. Can you see that, Chelsea? There is something out there. Differentiate it. It gives me x to the power of 5. There is something out there such that when you differentiate it, it gives me x to the power of 5. There is something out there.
Wait, I'm thinking.
What? Give that.
Hold on. Yeah, I don't know.
Okay, you know I said that it's always one notch higher than this.
Where?
Remember that? Remember that thing that I said? When you differentiate it, the power comes down. So if you're trying to work in reverse, it's always one notch higher than this.
So,
Try this. Try x to the power of 6. Differentiate x to the power of 6 for me. What would that give us?
6x5.
6.
Oh, add a 1 over 6x to the power of 6.
Of 5. Yeah. So can you see?
Yeah.
So it's always one notch less, isn't it?
Mm-hmm.
You see that? So if you're
Yeah.
trying to integrate something, it's going to be one notch more. You see that?
Yeah.
It's always going to be one notch more. So if you're trying to integrate to the power of a half, it's always one notch higher than to the power of a half. Can you see that, Chelsea?
Mm-hmm.
So what's your initial guess? X to the power of what? It's got to be one more than a half, because when you differentiate it, it's going to be one less. So x to the power of what?
3 over 2?
Yeah. So it's 3 over 2. Now let me try and differentiate this. So when I differentiate this, it will give me 3 over 2. The power comes down, the x stays the same, and then the power gets minus by 1. Oh look, it gives me x to the power of a half, which is the square root of x.
Yeah.
Can you see that?
Mm-hmm.
But I don't want this 3 over 2 thing. So I would go back to my initial guess and then stick the opposite of that, if that makes sense. So it's 2 over 3. I'm going to stick 2 over 3
Oh,
there.
yeah. I see what you
Okay.
mean.
So now when you differentiate it, look what happens. I'm going to keep this the same. Hang on, let me differentiate it. I'm going to keep that the same because that's just a constant. Remember, the power comes down, 3 over 2. The x stays the same, and then the power gets minus by 1. Can you see that?
Yeah. Mm-hmm.
What happens when you merge these two together? What happens when you merge these two fractions together?
It becomes. You have to make the denominator the same.
No, that's when you're adding.
Oh, you're multiplying? It will be 6 over 6, which is 1.
Yeah, 6. Yeah, that's why this whole block is 1. So it disappears. Can you see that? There, giving you square root of x. Okay, Chelsea?
Mm-hmm.
So let's start again here. Hang on. So we're trying to find the area from 0 to 100. Okay, Chelsea,
Okay.
of that square root graph. So for you to find the area, you would have to do what's called integrate. You have to integrate that. So when you integrate it, what would that give us? How do you integrate that, Chelsea?
I thought I already integrate. Oh.
Yeah. What was it? Can you remember? It was actually 2 over 3.
Oh yeah, 2 over 3
to the
x to the power of 2 over 3.
3 over
3 over
2.
2.
Yeah.
Oops.
From where to where, Chelsea?
From 10 to 0.
Oh, we're going to say from 0 to 10.
Okay.
Okay, Chelsea?
Okay.
All right. So now, what would that then give us? What do we do now? We've got to put the 10 into the x. Can you see that? Chelsea?
Wait. Can you repeat that?
You've got to put the 10 into the x, and then take away, and then put the 0.
Oh yeah. 0. So that would be just 1?
Wait, hang on. What would be 1? 0 to the power of 3 over 2.
The 3 over
Okay.
2 to the 0 to the power of 3 over 2 would just be 1.
Why?
Wait,
Why?
no. That would be just 0.
Yeah, but why? How do you know that?
Because if you times anything by anything, it's 0. Oh, and 3 over 2, when you're doing to the power, you times by itself. So 0 times 0 times is still 0.
Well, anyway, this thing here will be 0. You're right. What's this thing here? What's this block here? To work that out.
I don't know how to do that one.
Okay, hang on. What's in the past? I would give you something like this, Chelsea. What's 8 to the power of 3 over 2? How would you work this out? So we did this indices years and years and years ago. Can you remember how to work this out? What's that?
Don't you change it into the denominator to like a...
I'm going to change this. Whether 2 over 3. What is that? What is this as a number?
Wait, pardon? What'd you say?
What is this as a number?
What do you mean?
Without using a calculator, what is it as a number? How would you work it out? Do you know?
Oh, as a mixed number?
No, just give me, what is this? But at the moment, this is too complicated. What is that as a number?
I don't know what you mean.
Okay, what number is this?
8 to the power of 2 over 3.
Yeah, but simplify it. Because at the moment, you don't know.
As a number then.
Well, on the number line, where is it?
26 over 3.
Sorry?
26 over 3.
What? Say that again? 26
26 over 3 is the mixed
26
number.
over 3.
Is the mixed number.
No, it's not. It's not, Chelsea. Whether, hang on. What's x to the power of a to the power of b?
X to the power of a plus b.
No.
X to the power of a, b.
Yeah, x to the power of a, b. What's x to the power of a times x to the power of b?
X to the power of a plus b.
What's, x to the power of a plus b. What's x to the power of a divided by x to the power of b?
X to the power of a minus b.
Yeah. So let's start again here. What's x to the power of a to the power of b?
X to the
Chelsea.
power of a, b.
Yeah, x to the power of a, b. So you multiply these two together, right?
Yes.
So Chelsea, if someone gives you this combination of the two, you can actually break it up as two things. Okay. So what I'm trying to say here, Chelsea, is this complicated fraction, you can break it up as x to the power of a third to the power of 2, because you would just multiply these two together.
Oh.
Now,
yeah, I forgot about that.
What I'm saying is that this thing here is too complicated. So what's x to the power of a third?
2.
Yeah, that number's 2, and then you square it to give you 4. So after all that, this is a nice, neat number. It is the number 4. Okay.
Oh, yeah.
So if someone gives you if someone gives you a complicated number that you don't really understand, like this thing here, Chelsea, hang on, like this green box here. Can you see this green box?
Yeah. Oh, let me think. That's going to be.
Oh, sorry, not 10. Oh, we're not doing it from 2 to 10. We're doing it from 0 to 100. Remember, Chelsea?
What? Oh, why'd you make this part 100?
So, oh, sorry. I made a mistake there. So it should be 100. Okay, Chelsea?
100. Yeah.
Oh, well, wait. Going back to here, Chelsea. Why does this equal 1? Sorry, why does this equal 0? Earlier, you guessed it was
Oh, no, it's 1. It's 1.
No, it's
Wait,
actually
0.
0. Because 0, you can
times
break it
0
up.
is still 0 to the power of 3. It's still 0.
Yes. Explain that again?
If you break it up to 0, 1 over 2.
Yeah, which is the square root of 0, and then you cube it, it will still be 0. Okay?
Yeah.
So this whole thing here is going to be 0. So we're going to forget about this. Take away zeros. Useless, right?
Mm-hmm.
So what's this 100 thing to the power of 3 over 2? What is it?
That would be, hold on, let me think. 30,000. No. Wait, I did that wrong.
How are you going to break this up, Shoti? You're going to visualize
100 to the power of 1/2.
Yeah.
So that'll be square root of 100, which is 10.
Yeah.
To power of
10.
3. So that would be 300.
That would be what?
Wait,
No,
100
10
times.
10 times 10.
Yeah,
That's what to the power of 3 means.
Yeah. 100.
Right?
Oh, wait. 100 times 10 is 1,000.
Yeah. So it's actually 1,000. So we can imagine this as being like 2 over 3 times 1,000. And then this gets multiplied to the top, giving you what? Giving you what, Charles?
2,000 over 3.
Yeah, 2,000 over 3. So that's your area of that. Scroll back to our diagram, Chelsea. Scroll back to our diagram. So the area there is actually 2,000 over 3 precisely. Okay, Chelsea?
Mm-hmm.
We now have a way of working out the area underneath the curve.
Yeah.
Okay, Chelsea?
Yeah.
All right, how about this one? What is e to the power of x? What does that look like? Draw the graph y equals e to the power of x. Can you remember?
Wait, let me think about it. Wasn't it like, hold on, I'm thinking. It was, I don't know if negative, hold on, I'm thinking. It was like, wasn't it like, like this thing?
It is, yeah, it is
Oh,
like
okay.
that. Okay, so e to the power of x is something like this. So I'm going to say, work out the area from 0 to, let's say, 10. How do you do it, Chelsea? Work out this area.
Can you draw this symbol, because I don't know what this symbol is.
Okay, so the area is the integral and then something dx, and you don't know why it's this dx thing, and you don't know why there's an integral thing there, but you do know it should be from where to where. So fill in the blanks. What's the area, Chelsea? Fill in the blanks. What goes in here, Chelsea?
E to the power of x.
Yeah, e to the power of x. And then what? From
And then we
where?
have to.
No, from where to where?
From 0 to 10.
From 0 to 10.
Wait, why do you
Yeah.
put 0 at the bottom?
Convention. So we just came up with that way of doing it. So it's you start here and then you finish up here. Okay, so now the area equals what, Chelsea? So you have to do what's called integrate it. You have to
Okay.
find something.
Okay.
There exists something out there that when you
Oh, it's
differentiate,
going to be, let me think.
there is something out there in such a way that when you differentiate it, it gives you that thing. What is it?
I'm thinking, hold on. Uh, would it be like,
Do you want a clue?
yeah.
It's very easy.
What?
There's
What?
something out there that when you differentiate it, it gives you this. And the clue is that it's very easy.
E. What do I do with the E?
Well, you've got to differentiate it. Well, you've got to find something out there in such a way that when you differentiate it, it gives you e to the power of x. What is it?
Easy.
It's very easy. What is it?
I don't know. Something with E. E to the power of E. I don't know.
No, very close. What is it? It's very easy.
E. E to the power of E.
It's very, all right, it's not e to the power of e, but it's e to the power of ex. Is that a good
E to
clue?
the power of EX.
What?
E to the power of EX.
No, it's not e to the power of ez. It's e to the power of what, Chelsea?
X. 2X.
What? No, I shake my head with you, Chelsea. How do you differentiate e to the power of x? How
Isn't
do
it
you
like
differentiate e
X
to the
log
power of x?
X ln
No,
E?
no. How do you differentiate e to the power of x? Remember, we spent a lot of time looking for a base. That's when you differentiate it, it would be its exact same self. Remember that, Chelsea?
Mm-hmm.
There is well, in the past, we would search for a base here in such a way that when you differentiate it, it would be its exact same self, right? And it
Yeah.
turns out that we did
EX,
a lot of work
EX.
into finding out this base. It turns out to be 2.7 blah blah blah, and it goes on
Oh, it's the
forever.
same.
Yeah, so
Oh yeah,
we
I
just
forgot. I keep forgetting.
yeah, so we just give it a special letter E to represent that weird number. But the thing is, when you differentiate it, it will be its exact same self. So when you differentiate e to the power of x, it is e to the power of x. Right, Chelsea?
Yeah.
So when you integrate this, it will be its exact same self. Because if you differentiate this, what will it give you, Chelsea?
E to the power of X.
Yeah. From where to where, Chelsea?
From 0 to 10.
From 0 to 10. That then equals what, Chelsea? What do I write next? Something, take away something. What do I do now, Chelsea? Chelsea?
E, do I put the 10 into the X or the E? The X,
Oh,
right?
to the x, yeah.
Yeah. So then it would be E to the power of 10
Yeah,
minus E to the power of 0.
yeah. And
Then
what's
wouldn't
this?
that be E to the power of 10?
Wait. What's this block here?
1.
Yeah, 1. So what's the final answer?
E to the power of 10 minus 1.
Yeah, and that's your area from 0 to 10.
Oh,
You get it?
yeah.
Okay.
Just like,
How do you, so revision time now. How do you differentiate 1 over 1? Hang on. How do you differentiate
oh, sugars.
how do you differentiate natural log of x?
Natural log of X.
Yeah.
Differentiate.
Yeah, how do you differentiate it? What's dy by dx?
Wait, I know this one. This.
Wait there, I've got to check everything, Chelsea. How do you differentiate sine of x?
Hold
How do you differentiate? Oh, I don't trust you. Y equals cos of x. How do you find dy by dx of all of these? Okay, let's do the kindergarten one
I know how to
first.
do it though. I know how to do. Oh,
Do the kindergarten.
sine x.
How do you
One.
differentiate sine x? What?
One.
No. How do you differentiate? How do you differentiate? How do you differentiate sine of x?
Wait, hold on. Thinking. I don't.
Shake my head.
No, just let me think, cause I know it. I just need a little push, a little thinking.
Give up.
Oh! I know how to do it.
How do you differentiate sine of x?
Just give me a second to think. Okay, so you have to do limits.
Oh, that takes yonks.
Oh.
You have to use limits to work it out, but we spent ages and ages. We got to a point where we can just differentiate it straight away. It's
One.
going to be of x.
Cos.
When you differentiate,
And then cos of x is negative sine x.
yeah, negative sine of x.
Yes.
And now there's no way in the world you can get this one if you can't get the sine one. How do you differentiate natural log of x? It turns out to be 1 over x. 1 over x.
Oh yeah, I just looked at my notes just now. It's 1 over x.
Yeah, but why? How do we know it's 1 over x?
Because when you differentiate it, it becomes 1 over x.
How do we know that? The way we did it was from here, Chelsea, you would exponentiate both sides equally.
Oh.
And that will then give you this, right? Because when you exponentiate the right-hand side, it's actually e natural log of
log
x.
x. Yes.
And then these two, in a way, they cancel each other out, right?
Leaving you.
So
Yeah.
now you can use implicit differentiation. So go and differentiate. See, differentiate the left-hand side. What does that give us?
Why? Shit. I mean.
What was that, Chelsea? I bet you swear a lot in school now, don't you?
Oh yeah, I do.
Oh, what?
And around family too.
Oh, what? Not around your uncle. Differentiate e to the power.
Okay, so from here, you differentiate it. Then that would be e to the power of y times dy dx.
Yes. And then how do you differentiate the right-hand side?
It would just be 1.
Yeah, 1. And now your job is to get dy by dx on its own.
So then you divide 1 over e to the power of y equals dy by dx, but then you go back. So then,
we don't want the answer in terms of this.
Yeah, so
we don't
then
want
that becomes 1 over x.
Yeah. So if you go back here, you can see e to the power of y is that. That's why when you differentiate this, it gives you 1 over x. Okay, Chelsea? Okay. So now
I remembered.
Okay. What does this graph look like, Chelsea? Y equals 1 over x squared. Scroll up a bit, Chelsea. What did you say you were doing in school at the moment?
Surface area and volume.
Oh, okay. Come on then. So how do you do this? Oh, so yeah, what does this graph look like?
Wait, I'm thinking. Isn't it like... Okay, so 1 over x is like this. X squared is like that.
Yeah.
1
over x squared. To the power of 3 looks like this, your favorite, apparently.
I'm not talking about 1x to the power of 3 though.
Yeah, but what's 1 over x squared? You can always plot it, Chelsea. Let's say when it's negative.
It's this one.
Yeah, I'm just going to prettify it. Okay, I'm going to draw it like.
It's already pretty.
Okay, so now Chelsea, work this out from 1 to, let's say, 10. What's this area here?
Hold on.
What's the area? So it's going to be area equals. Can you equals what, Chelsea?
Equals to sigma.
Can you do the integral sign?
I don't know how to draw it.
Oh, go on, try and copy that. It's just a long S.
Oh, okay.
No, not OS. I just told you that. Yeah. Have another go. Okay, and then it's going to be something. And then what goes in here, Chelsea?
What? You
What
mean
goes
the
in?
boxes?
Yeah. What's this? What goes in this bubble?
I don't know.
Well, it's going to be something dx, and you don't know why this dx exists for the time
Oh, I
being.
forgot about that.
Yeah. And then
That'll be 1 over x squared.
yeah, 1 over x squared. And then what goes in here and what goes in here?
1 to 10.
Yeah,
10.
1 to 10. So now what do you do, Chelsea? Well, now equals what? And then
Equals.
the squared bracket, right?
We have to differentiate or like
No,
integratory.
you have
Or
to
what's it called?
integrate.
Integrate. Integrate 1
Yeah,
over x squared,
yeah. Which
which
means
is negative. It's negative or x to the power negative 2.
x to the power of negative 2. Oh, that's the moment, right? Oh,
Yes.
so we change to x to the power of negative 2. Same thing. You see that?
Mm-hmm.
Okay. So how do you integrate it? Well, integration means you've got to look for something in such a way that when you differentiate it, it gives you this thing here. What is it, Chelsea? There is something out there such that when you differentiate it, it gives you x to the power of negative 2. What is it?
Oh, this is. Let me think for a bit. So, 1 is negative 1x to the power of negative 1.
Like this.
Yes.
Okay, so I'm going to try and differentiate it. Okay, Charles? So when I try and differentiate it, the negative 1 comes down. That will give me positive 1. The x stays the same. The power gets minus by 1. So indeed, you're correct. Okay, Charles?
Wait.
Charles?
Wait, I'm thinking. Wait, did I do that right?
Yes.
Okay, I didn't think I did that right.
How did you get it right without knowing you got it right?
I don't know. I just kind of guessed.
Okay, so what do I write in here, Chelsea? Well, don't forget, it's always 1 notch higher than this negative 2, isn't it? So it has to be something with the form x to the power of 1 notch higher. Can you see that, Chelsea?
Mm-hmm.
But anyway, what now, Chelsea?
Um,
Uh,
okay, I'm
so
thinking.
when you
It's going to be, I don't know, negative.
Chelsea integrated it earlier from 1
Oh,
to yeah.
okay, okay.
But then
10.
let's tidy this up. This is x. This is what, Chelsea?
X to the power of negative 1.
Yeah, which is this? Can you
Oh,
see
1
that?
over x 1.
Yeah.
Yeah. Mm-hmm.
Okay, now what, Chelsea?
So then you do negative 1 over 10
Negative 1 over 10, and then
minus negative
minus.
or plus negative. Wait, yeah, plus.
Okay,
Just plus.
plus what?
Plus 1 over 1. So
Yeah,
1. So
yeah.
then
So
it
that
would equal 0.
why
Oh,
equals
no,
0?
it equals 9.
No. In order to add or take away fractions, the two denominators have to be the same.
Yeah,
Chelsea.
I changed it.
Oh, so this would be 10 over 10. So that would be
9 over 10. Negative, no, positive 9 over 10.
yeah. So that's your area underneath that.
Mhm.
Okay, Chelsea. So
Yeah.
now next one, Chelsea. 1 over x. What does that look like? Y equals 1 over x. Cool. So I'm just gonna prettify it.
Prettify it.
Yeah. So from 1 to, let's say, 2. What's this area here, Chelsea? What's this area? So that area is equal to the integral of 1 over x dx from 1 to 2. Are you okay with that?
Okay.
So the question is, how do you integrate that, Chelsea?
So the integrated version of 1 over x would be
Yeah, so can I change this to negative 1? Is that okay?
huh? Yeah.
Yeah. So you got to look for something in such a way that when you differentiate it, it gives you x to the power minus 1. What is it? There is something out there that when you differentiate it, it gives you 1 over x. What is it?
Let me think. Negative 2x to the power of 2?
Okay, like that.
Wait, no, negative 2. X negative 2.
Negative 2. So now when I differentiate this, the negative 2 will come down. So that will give me positive 4. The x stays
Never mind. Hold on.
minus 1. You've given me x to the power negative 3. I want negative 1. And you've given me
0 to the power of x.
Wait, hang on. What is it?
0
0
to the
x.
power of negative 2.
So 0 times anything, it would be just 0. So what you've given
No.
there is
X
something else
minus
in that.
1.
That
What the
when you
hell?
differentiate this, it gives me x to the power 1. There is something out there that when you differentiate it, it gives you 1 over x. What is it?
I'm thinking. Hold on. Man, I don't know.
Well, it's got to be one notch higher than this, remember, Chelsea?
So 0?
What? Like x to the power 0?
Well, you said one notch higher. Higher than negative
Yeah.
1 is 0.
You know the pattern in the past. If I were to ask you to integrate x to the power 7, you have to think about x to the power 8, right?
Okay. Yeah.
If I were to ask you to integrate x to the power of, let's say, 13, you would have to think about x to the power of 14, right, Charles? Because when you differentiate x to the power 14, it would be 14x stays the same, the power gets minus by 1, and then you would somehow get rid of this 14. So when you integrate, it's always one notch higher. Can you see that, Chelsea?
Yeah.
But then if you do this, Chelsea, if you integrate this, one notch higher would be 0, but x to the power 0 is always 1. And when you differentiate 1, it gives you nothing. So how do you got to look for something. Hang on, Chelsea, hang on. Let me give you this diagram. Can we overrun the lesson by 10 minutes?
10? Yeah.
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 You're not going to have a heart attack, are you? If we
No,
overrun
it's
the
fine.
lesson by 10 minutes.
It's fine.
Anyway, Chelsea, wait there, Chelsea. When you differentiate x to the power 4, say, it will give you x to the power 3. When you differentiate x to the power 3, it will give you x squared, something along this, 3x squared, right? Notice that if you want to integrate x to the power 3, you have to think about x to the power 4. If you want to integrate x squared, you have to think about x to the power 3. Okay, Charles?
Yeah.
Let me just draw this diagram. X squared, when you differentiate it, it will be 2x there. Right, Charles? And if I were to ask you to integrate, let's say x to the power minus 4, you have to think one notch higher. You have to think x to the power of
-3.
minus 3. You see that, Charles?
Mm-hmm.
So when you differentiate this, it will give you something of the line x to the power of minus 4.
Yeah.
When I give you when you try and integrate x to the power of minus 3, you have to think about x to the power minus 2. It's always one notch higher, right, Charles?
Yeah.
So what happens when you try and integrate x to the power minus 1? It's got to be one notch higher, but then this is just a number, right? Charles, there's
I'm
something.
still confused. I don't know like what x to the power -1 is.
Yeah, well, wait there. X squared here, you have to think about x to the power minus 1. That will give you x squared, x to the power minus 2, right?
Mm-hmm.
X to the power minus 3, you have to think about x minus 2.
Yes.
So what is it that gives you x to the power
It's
minus
supposed
1?
to be x to the power of 0, but that just turns to 1.
Yeah, so what do we do?
X. I don't know. X to the power of 2?
Charles,
-2?
I always get you guys with this trick, Chelsea. It turns out to be
You can't do
natural
it.
log of x for some
Oh.
reason.
어떡하
How do,
now?
how do you differentiate natural log of x?
Yeah.
How do you differentiate natural log of x, Chelsea?
It's 1 over x.
Yeah, 1 over x.
Oh!
So it's kind of weird. This pattern's kind of weird because if you look at it, it's always one notch higher. Can you see that? It's always one notch higher. It's
Yeah.
always one notch higher. It's always one notch higher. It's always one notch higher. But for some reason, when it comes to 1 over x, this weird natural log crops up. It breaks a pattern. Can you see that, Chelsea?
Yeah.
So, to integrate it, Chelsea, so what do I put in here, Chelsea?
ln x.
ln x, yeah, natural log of x. So what's the area, Chelsea?
ln 2
Yeah,
minus ln 1.
ln 2 minus ln 1. Do you know what ln 1 is? What's this block here?
Isn't that just... Wait, I'm trying to think of our previous lessons. You told me this, right?
Yeah. Shall I remind you?
No, I think... Is it
It's
0?
like me asking you. Well, you have to explain rather than guess. It's like me asking you this. What's log base 2 of 8? You can't remember what that is, right?
Yeah.
So so what is this block here? So your eyes has to zoom into the base. So you've got to translate it. 2 to the power of what will give me this number here?
Oh, 2 to the power of 4. 3, 4, 3.
Yeah,
2 times
3.
2.
The
3.
whole log block itself is talking about this index.
Oh!
Yeah? So when you try and translate natural log of 1, your eyes zoom into this e here. That's the base, e. Okay, Chelsea? You have to translate it. E to the power of what will give me 1. What is it?
0.
Yeah, anything to the power of 0 is 1.
Oh, so then the answer is 0 because the missing part is 0.
So this is actually take away 0.
Yeah.
Okay, Charles? And then this number here is actually the number. This here is just a number. Who cares what number that is? It's just a number. You can just punch into a calculator. So that area there, Chelsea, is natural log of 2.
Oh. Okay.
No, yeah. So that area there is natural log of 2.
Okay.
Okay, Charles?
Yeah.
To end the lesson off, do the integration sign for me. What does it look like?
Isn't it this? Actually, I don't remember. Isn't it this?
No, that's a summation. Well, if you want to find the area of something, Chelsea,
it's
gonna be
this thing.
is this it's this long S thing.
Long S.
Can you somehow prettify this? Find a way of prettifying it. Look at my one. It looks really pretty. Look at your one. It looks ugly.
If I try, it could be pretty.
Try to turn it into a nice looking S somehow. Okay, good thought.
Mhm.
And then if you want to find the area underneath the x squared, it would be x squared. And then what goes in here, Chelsea?
dx.
Dx, which we will look at in the future. Okay.
Okay. Mhm.
Uh, and then from whatever to whatever. Okay, Chelsea?
Yeah.
So you now have the ability to work out the area underneath a curve by just integrating it.
Yeah. Okay.
Okay, Chelsea?
Mhm.
So I see you next week. Okay, Chelsea?
Are you sending me homework?
Do you want homework?
I'm just saying, if you do send me homework,